Hello, this video is entitled Tangent and Normal Vectors. Now in the video for velocity and acceleration, I had mentioned that the velocity vector is the tangent vector. So r prime of t automatically is your tangent vector. Now we're going to take that one step further and we're going to define something here called the unit tangent vector. All right, well, earlier in this course, we learned what a unit vector is. So the unit tangent vector would just be a matter of taking the tangent vector and converting it to a unit vector, which is always done by taking a vector and dividing it by its magnitude. So we use this capital T to represent the unit tangent vector. So in other words, r prime of t is perfectly fine notation to represent the tangent vector, but the unit tangent vector does have this reserved variable capital T here. So essentially it's t of t, where little t is the value at whatever time. So you take r prime of t divided by the magnitude of r prime of t. And then they're just telling you that r prime of t, of course, cannot be the zero vector, because you would have divide by 0. And this is true for both plane or space, so we don't need any kind of separate formulas. So in this example, I'm saying, okay, find t of t and t of 1 for the position vector r of t equals t cubed, comma 3t squared. All right. So we have to get the tangent vector, which is just the derivative. T cubed is 3t squared. 3t squared is 6t. And the magnitude of r prime of t will be the square root of 3t squared, which will be 9t to the fourth, plus 6t squared, which is 36t squared. Now, I don't know why I did this. You got to be careful that you know what you're doing here. You can't split those into separate radicals. In other words, the square root of a plus b is never the square root of a plus the square root of b. Well, if the numbers are like 0 or something, but in general. So I factored out, I don't know why I did this, but the square root of 9t squared, because they both shared that in common. But when it factors out, of course, it has the radical with it. And that gives me a 3t. And then when you factor out the 9t squared, you're left with t squared plus 4, which does not simplify, but the square root of 9t squared would be 3t, and we're assuming that t is positive here. Technically, the definition of t squared is actually the absolute value of t. Well, anyway, so here's the velocity vector and then 1 over the magnitude. So 1 over that magnitude we just found right there, and I guess it just kind of cleaned up a little bit better by doing it this way. It doesn't make it any more right, but so 3t squared over 3t would just be t, and then with the square root of t squared plus 4 on the bottom, and then 6t over 3t would be 2 with the square root of t squared plus 4 in the denominator. So that's your unit tangent vector for any value t. It's going to give you, whatever you put in there for t, it's going to give you a different vector, but it will be a unit vector. You can check that out real easily. But this one we said find it at 1. And you put 1 in there, it's going to be 1 over the square root of 5, and then 2 over the square root of 5. I didn't bother to rationalize the denominator, but my point being, like I said, it would have been a unit vector for any value t. If I'd have put 5 in there, it would have been 5 over the square root of 29 and 2 over the square root of 29, which you can check and see that that's a unit vector pretty easily. All right, I just showed off some maple stuff here. Don't worry about any of that. Yeah, okay, I made it. Yeah, I made it simplify the answer and to make it look like what I got. It did. So, but there it is. There it is at 1. So they rationalized it. So 1 over the square root of 5 is the same thing as square root of 5 over 5, and then 2/5 square root of 5 is the same thing as 2 divided by square root of 5. All right. Now we're going to find the unit tangent vector, and then we're going to find a set of parametric equations for the line tangent to the space curve at that P. So let's find the unit tangent vector first, and here's an example of they give you the point. When they give you the point, we have to figure out what the t is going to be, which is usually not too difficult, especially this one's really not difficult. If this is the t and that's a t and you got 1 and 1, geez, I bet t would have to equal 1, wouldn't it? You could check that last one, but it's really, already pretty much determined right here. So first two derivatives are super simple. They'd be 1 and 1. Here you got to use a little chain rule. Bring the 1/2 down, makes that t to the negative 1/2, 4 minus t squared to the negative 1/2. And then the derivative of the inside will be minus 2t. So if you put 1 in there, r prime of 1 would be 1, 1, negative 1 over root 3. And then the magnitude of that is going to be 1 plus 1 plus 1/3 when you square this term, which is the same thing as the square root of 7 over 3, or you can split them up. Now what happens here is the unit tangent vector, if you're dividing by this, so 1 over this term right here would flip these two over, make it like that. So it's fine if you leave the constant out. Mathematically it's fine, or it can be distributed. Either way. Looks like I decided to give the Aggies some love here with this one. Now I want to mention, let me just kind of make something clear here. We're going to find the parametric equations of the line. Now we don't need specifically the unit tangent vector to do that. I just want to mention this. I think I did go ahead and use it just for consistency, but really I could have just used the tangent vector, because keep in mind the unit tangent vector is going the same direction as the tangent vector. It just has a length of 1. Remember, to come up with parametric equations of lines, we just need the direction vector. Its length is irrelevant. So I could have used for as far as this goes, I could have used, where was it up here? I could have used 1, 1, and then negative 1 over root 3 as my ABC for the parametrics, and it would have been correct. Because we just needed the direction. But part of the problem was asking for the unit tangent vector, so that's why I found it, because we needed it for the problem. But we did not need it to get the equations of the line. So there we go. So you have 1, 1, square root of 3 was our point value, x0, y0, z0. Then I did use the 3 results right here. Except I kept them under one radical here. Not that that matters, but so there we go. Oh, here's a graph coming up of them. Just thinking about maybe I should have graphed that one in Maple, but looks like I got one coming up we can look at. But like I said, it's I'm not responsible for any of that, but I think the visual part's kind of fun to look at it and see. Okie doke. Well, this one may be maybe a little more challenging to find the value t here, because I guess what makes this one interesting is that to solve for 2 sine of t equals 1, that means sine of t is 1/2. That means t could equal, now we're assuming not infinite answers here. We're strictly saying between 0 and 2 pi. It doesn't say that in instructions, but you can kind of go with that. We don't need to have the plus 2n pi business that you learned in trig. But anyway, going back to the sine of t equals 1/2, that would occur at either pi over 6 or 5 pi over 6. So that doesn't really help us. It just kind of narrows it down to 2 of them. But then as soon as you get to this middle one, cosine of t equals the square root of 3 over 2 positive, it would have to be pi over 6, because you can't be 5 pi over 6 because that's in quadrant 2 and cosine is negative. So that's what actually narrows it down to being pi over 6, is both of these first two. And then just as a formality, you can plug it in here and see that it's right. Maybe it was a little more challenging, but even then it Wasn't all that bad. So how about the derivative? 2 sine of t be 2 cos t. 2 cos t would lead to negative 2 sine of t. And then be careful here because chain rule. You bring the 2 down, that makes that 8 sine t to the first, but then you're taking the derivative of sine of t with that. So that's what's causing the cosine of t at the end. Think of it like this, think of it as being if you were taking the derivative of 4u squared, where the u is sine. The derivative of that would be 8u du. So therefore, 8u sine du cosine. How about that? Isn't that fun? And then put in pi over 6. Okay, that's just numerical calculations. I got root 3 minus 1, 2 root 3. Took the magnitude. Well, that worked out to be a nice convenient little 4 there. When you square each of those terms, you get 3 plus 1 plus 12. Square root of 16 is 4. So the unit tangent vector would be 1/4 times this tangent vector. Or, you can write it as one vector, all divided by 4. Square root of 3 over 4, comma, negative 1/4, comma, root 3 over 2. Now here's what I was saying. I'm not trying to confuse you here with two answers, but it's based on what I was just saying a few minutes ago. That I can use, the bottom one's actually using the unit tangent vector, and the top one is using the tangent vector. Both would be correct. Oh, and there's the unit circle from, I guess that should have been on the other page there, where you could have seen the pi over 6. No big deal, but I guess I didn't have room for it. So either one of them. So I did some fancy maple stuff over here. I made that dot ginormous there. I guess I can erase this part. I must have just circled this before, but I didn't have to save it for anything. Probably just pointing something out. Let me zoom in on this a little bit just so you kind of see. So, yeah, that point is giant. Well, you see that purple, faded purple looking, there's your tangent line, and you see the black vector, that's your tangent vector. Actually, it's the unit tangent vector. But look at the equation for the line. I didn't even use the unit tangent vector. I used the regular tangent vector. Because remember, the line goes on and on forever. It doesn't really matter. So yeah, that worked. But then the graph, the maple produces the tangent. They produce them as the unit vectors. And I guess I circled that because we're about to talk about this one here in a second. Let me see if there's another example of this, or we're going right into this. Yeah, so there's the tangent line. That looks really good. They're running right along with that tangent vector. Well, heck, I might as well just tell you. That's what this is right here. The green one's the unit normal vector. I call it principal unit normal vector. I just call it the normal vector, unit normal vector. And so obviously it's perpendicular to the tangent vector. Now this one will go inside the curve, inside the curvature of the shape. I mentioned in another video that acceleration does that. I couldn't say 100% sure of acceleration, but with this one I can for sure. Now look at this formula. Formula looks harmless enough, but it can be extremely rude to evaluate this. I mean, algebraically, it can be a nightmare. So I'm going to show you a couple of techniques how you can find this unit normal vector, whether it's plane or space, or two different techniques. And without having to use this formula. But anyway, here's what the formula is. It's the derivative of the unit tangent vector over the magnitude of the unit tangent vector. Now, when I say difficult algebraically, I'm talking about it because to get you can't have numbers. Well, you have to have values of t to be able to take the derivative before you can plug the numbers in there. and it can get really kind of messy. And let's take a look. Yeah, so here's what I'm talking about. That's what I'm saying about inside the concavity of the curve. Because if you look at this from a normal vector standpoint, you see where this tangent vector is right here. Uh, a normal vector could be, coming down this way, 180 degrees across, and it would be normal, but it wouldn't by definition be this n of t. It wouldn't be the principal unit normal vector. Same over here. You could have a vector going the opposite direction, and that would be normal to the tangent vector, but it would not be the t of t. Now here's one interesting idea, because they are normal to each other. If you were finished working a problem and you were trying to check to see how you did there, whatever, well, obviously n of t dot t of t has to be equal to 0 to be normal to each other. Now, I'll show you how to do this without, here's one for a plane. So this is without having to use that formula. So this is t cubed I plus 2t squared j at t equals 1. I just kind of let the calculator graph the parametric curve. Then I drew the t of 1 after I evaluated it. So I found the positions here, which I could have plotted them manually. So there it is at when t equals 1, you're at the point 1, 2 right there. And it goes on to 8, 8. So that's good enough. That covers the 1. So now let's look at this, and r prime of t is going to be 3t squared, comma, 4t. So when you plug 1 in there, that means it's going to be 3, comma, 4. And then the magnitude of that is going to be the square root of 3 squared plus 4 squared equals 5. So your unit tangent vector right here, t of 1, is going to be 1/5 times 3, comma, 4. So it's going to be 3/5, comma, 4/5. Now, to get that normal vector, the principal unit normal vector is only going to be two possible answers. See, it's still got to be a normal vector. I mean, obviously, you could find infinite vectors that would be normal to that, but they would all have different lengths. They wouldn't have length of 1. So I want to keep the 3 and the 4, because what would happen, and the 5 especially. So it's got to be one of these two choices. In other words, you switch the two numbers and you change one of the signs. So I switch these two, and I can make the 4 negative, or switch those two and make the 3 negative. Because look at the dot product real quick. In fact, I'll just skip the denominators. Negative 4 times 3 is negative 12. 3 times 4 is positive 12. They would add up to 0. Then you have 4 times 3 is 12. And negative 3 times 4 is negative 12. They add up to be 0. Like I said, there's lots of numbers that would do that, but only by keeping these divided by 5, like these ratios, allows them to still be unit vectors. Yeah, for example, the vector just negative 4, comma 3 would be a orthogonal vector, but it's not a unit vector. It would dot to be 0, but it defeats the purpose of not being a unit vector. So there's what you do for plane. Space will be different. Plane, you just switch them and change their signs. So it's got to be one of these two. Now this is where you'd want to graph these. Like I said, with 2 space, they're easy to graph, so it's not that big a deal. Kind of do what I did here. You can let the calculator draw it. And your graphing doesn't have to be perfect. But what you would do is you'd kind of sketch it like I did, and then to know which one's going to be the unit normal vector, it's going to be the one that goes inside the curvature, not away from the bend. Along with, the bend is covering around it there. So it's got to go this way. All right? Now, we've narrowed it down to one of those two answers. So we have to figure out when a vector is going that direction, what would be the value for the x component and what would be the value for the y component. Well, if it's going down and to the right, that means x is moving in a positive direction and y is moving in a negative direction. So that's the answer I would want to pick. Therefore, it has to be this one, because the x direction is positive, the y direction is negative, and then there it is. There we go. That would be our principal. Yes. Now I'll scroll down for this. I'm not going to go through all the steps on this because it looks harmless enough. You're probably thinking that can't be hard to use that formula, can it? A lot of algebra. So I'll go slow enough somebody wanted to pause this video and look at these steps. So I'm getting r prime of t. So we can't plug in numbers until after we've simplified this. Yeah, this is the fun part when you get to this t prime of t right here. And plus you get these quotient rules. Because, yeah, you're going to have quotient rule and chain rule and all kinds of other mess. So you see it gets kind of sloppy down here, and now it's kind of tidying it up. Oh, and then I got to get the, yeah, so that's just t prime of t to get that. Then you got to get the magnitude of t prime of t. Which then you take t prime of t over the magnitude of t prime of t, and you come up with this result that I simplified. Then if you plug 1 in there, you do get exactly 4/5, negative 3/5. So the disadvantage to the method I did is you're going to have to choose between one of two vectors, but that's not that difficult compared to this, I don't think. So this formula will directly calculate the answer. Now, one thing I'm going to say, I guess that would have been a little simpler, and I mentioned this right down here. I guess I was saying if you're trying to find n of t just as a function of t is extremely complicated. It's a little bit easier, though, than what I did if you know you're finding it at a value for 1. So you could go back and try that, or did I do that? No, I did not do that, but I'll just explain it to you. But as a function of t, it's very complicated. But yes, once I had t prime of t done algebraically, yeah, I had to do all this algebraically right here. I had to get to this right here. And whether you simplified it or not, that doesn't matter. But I had to get to this algebraically. But yes, I could have plugged 1 in at that point and got t prime of 1, and then got the magnitude of t prime of 1 numerically, and then divided, and that would have been correct. So let me just look at this real quick. If I put 1 in here, what's the bottom? It's going to be 25 to the 3/2, which is the square root of 25, which is 5 cubed, makes it 125. All right, I'm using a mouse pad to do this instead of a pen, so this is going to be kind of messy. This would be 48 over 125. And then put in 1, that would have been negative 36 over the same 125. So I'm not going to write that again. Okay. Oop, that's a pretty terrible looking 6. Negative 36 over the same 125. Then I could have put 1, taken the magnitude of this vector, which the numbers are a little large there. But anyway, well, let's just say, since it's already simplified, I'll put 1 in there, which is 12 over 25. But yeah, you could have done this number squared plus that number squared, square root. However, I'll just show that t prime of 1 magnitude would have been 12 over 25. So 48 over 125 divided by 12 over 25, yeah, I can see that that's going to be 4 over 5. And then over here, it's going to be negative 3 over 5. So yes, okay, so it would have been a little simpler if you use that formula, but still, t prime of t is still a mess, even if you didn't have to do these last couple steps. So that's what I was just saying there. So yeah, that was a pretty basic looking, wasn't even a difficult starting point. What was that vector valued function again? It was like t cubed 2t squared. That looks harmless enough. Yeah, that magnitude is always going to have that square root in there, so that makes the quotient rule fun when you got the chain rule in there. And I guess I was having some fun here. This is not the example we just did. I just did one in space where I used sine, cosine, and then t as the three components. And then what I did is I told I think it's doing it at every starting at 0 at every value of pi. It's graphing the tangent vector in black, the unit tangent vector, and then it's plotting the normal vector in green. So here'd be the first one you see. So you see the unit normal vector is going inside the curve. Here's the next one up here, inside the curve. There's the next tangent vector. The green one's inside the curve. See what I was saying? There we go. There's that one at 3 pi, goes here. And this one's tangent, and there's the normal inside the curve at 4 pi. So once again, you don't have to worry about graphing that, but I thought it was fun to look at. Tangential and normal components of acceleration. Alrighty. The tangential and normal components of acceleration are scalar values, a sub t and a sub n, meaning that your acceleration vector can be written as an equation a of t equals, well, there's another a, but it's a different a. A of t on the left is a vector, so a of t is a scalar, so a of t is a multiple of your tangent vector, unit tangent vector, plus a of n, which is the normal component of acceleration, times your n of t. Let me explain this little picture over here, and then we'll look at the formulas. Well, let's say that you had at this point, I won't worry about both sides, we'll just look at this one. And let's say your n happened to go this way, right here, because it's a length of 1 in normal vector. There's your t, and let's say your a happened to look like that. So using the idea of adding vectors together geometrically, you could extend this n out to right here, to where I got the dot right there. I'll put a dot there for a second, I'll change it. Then you can extend the t out to here. So if I now add this vector plus that vector, which could then be moved right over here, I would get my acceleration vector. Well, the values that you multiply the n and the t by to stretch those vectors out to add to the a vector are those components of acceleration. They are a of t and they are a of n. So that's what they do. They stretch them out and to where you can add those. See, so in other words, so t plus n obviously does not give you a, but then when you multiply them by their appropriate components, it does. So they have different formulas for these. I'll just show you what I recommend using. Or there's only one that I recommend not using at all. All right, so for the a of t, there's 3 different formulas. I've never used this first one, or maybe once or so. These other 2 are good, especially this one here. You'll see when I do a problem. The tangential component of acceleration, if you do the acceleration vector times the tangential vector, tangent vector, you can dot that, or you can do v dot a divided by the magnitude of v. I don't know, I wouldn't worry about that. A dot t works well. Now for the a sub n, this is the only one I would recommend not using, because I'll show you why here in a minute. Because getting that n vector is a pain. Which we're going to find the n vector, but we're going to do this one without using that formula. T prime of t divided by the magnitude of t prime of t. So as I was telling you before, I was going to show you, 2 ways. For the plane vector, I showed you how to get n of t without the formula. Now I'm showing you how to get it without that formula for a space vector. I don't usually care for this one, although it's not that bad. V cross A, magnitude over magnitude of V. But I like this one right here. Now, of course, this one implies that you've already found the a of t first, which I always do anyway. So it's the square root of the magnitude of the acceleration vector squared minus the tangential component of acceleration squared. So let's say that we want to have a problem and we want to find n of t. Here's what I think, without using that ugly formula. Here's how I would do it. We have this equation that has 5 unknowns in it. A of t on the left side is easy to get. It's just the second derivative of the position function at some value t. A sub t, the tangential component of acceleration, is not hard to find. T of t is just the unit tangent vector. That's not too bad. A sub n is not too bad from that formula. So what we do is we find those 4 components, then we just algebraically solve for n of t. Just treat it like a little algebra problem instead of using that complicated t prime of t over the magnitude of t prime of t. So that's what we want to do. I'm wondering, just out of curiosity, I can't remember if I did try to work that problem out the ugly way. I might have and given up. No, it doesn't look like it. I did it sort of in maple, kind of, but maybe one of these days I'll try it at the end and add it in this video. Yeah, it's because in class, teaching a face-to-face class, it's just too much time involved for something that I don't require the students to have to do. But I should issue myself a challenge and try it sometime. Like I said, I can always add a new clip at the end of the video. Alrighty, so what are we saying in this example? Find a sub t, not a sub t, I'm sorry, a of t, acceleration at t, unit tangent vector at t, a sub t, that scalar, a sub n, and then n of t at t equals 1 for this position vector right here. So we're going to get n of t last, because we're going to solve for it algebraically. The other 3, we're kind of using the formulas and the rules and stuff. So there's the equation. And here it is at 1, of course. Now, I don't have any values there, but obviously the a sub t and the a sub n are also evaluated at 1. They just don't define them as, they didn't put them as parentheses of t. They just wrote at and an. See right there. But yes, everything's at 1. It's not like something would be at 1 and these would be at 2 or something like that. So acceleration vector, the left side, super duper easy. Well, especially when the functions aren't too gruesome. I don't like one to be too gruesome. I guess anything could be challenging if they were ugly functions and the derivatives were ugly, but this one's super easy. The derivative of t cubed, 2t, 4t squared for velocity would be 3t squared, 2, 8t. And therefore the acceleration then will be the vector of the derivative of the velocity. Also r double prime of t, which I did not write that, but I wrote r prime there, but it is r double prime. 3t squared would have a derivative of 6t. 2 would be 0. 8t would be 8. A sub 1 would be 6, 0, 8. So there's your left side, 6, 0, 8. Now let's get the unit tangent vector. So we don't have to do this algebraically. We can do it because we know t equals 1. So we can just plug 1 into r prime. See, r prime is just the tangent vector. R prime of 1 is a tangent vector, so it would be 3, 2, 8. And then we need the magnitude of this because we have to convert it to the unit tangent vector. So square those, 9 plus 4 plus 64 will be 77. So the unit tangent vector is 1 over the square root of 77 times 3, 2, and 8. I guess I didn't want to use the space to distribute it through there. Obviously, it could be each term here divided by the square root of 77. But that's a correct answer. So now a sub t, we're going to use this formula right here. A dot t. See, this is easy because we already have a and we already have t. So just dot them together. Now, when you dot something like this with a scalar multiple, you can leave the scalar multiple there and then just dot these numbers, so you don't have to distribute it, then dot product it. In other words, 6 times 3 is 18, middle one's 0, 8 times 8 is 64. So 18 plus 64 is 82. And then you bring in the 1 over root 77, so it's 82 over root 77. And then I showed the square root formula also. Oh, I'm sorry, but we're doing AN, excuse me. It's not a different formula. So yes, I'm using the square root formula, which is the one I said earlier that I kind of like. So we're taking the magnitude squared of the acceleration vector. So when you square the magnitude, all you're basically doing is you're getting rid of the square root. So it would just be 6 squared plus 0 squared plus 8 squared, which is 100. And then here's the a of t that we just got right here. So that would be 82 squared, which is 6724. And then, of course, the square root of 77 squared would just be 77. And what I would have done here, I didn't show it, but get a common denominator. 7,700 over 77. Subtract, you get 976 over 77. I don't know how I realized this was true, but it is. But it's okay if you didn't simplify it. That's fine. Somehow I figured out that 16, maybe I just thought 16 might go into it. I just checked it in my calculator, so I reduced it and got that 4 out of there, the square root of 16. So now we have everything we need. So we have A1 equals ATT1 plus ANN1. Now we algebraically solve for N1. So here was A1, 608. Here was the AT, 82 over root 77. The T1 was 1 over root 77 times the vector 328. AN we just got right here is 4 root 61 over root 77. Or like I said, if you didn't simplify that radical, that would be okay. So what I did now is you multiply these. I multiplied these two together to get 77. Then so I took this whole thing, which will now be 82 over 77, and I multiplied it by these three numbers because now I need to algebraically combine two vectors by addition and subtraction, so I don't want that scalar out there. So you take the 82 over 77, distribute it times 3, 2, and 8. You get these three numbers. And then now I take 608 minus this vector that came from this side. So to combine these two vectors, I need to get a common denominator, get 77 over 77 here. So you can do the arithmetic here, but basically 6 times 77 minus 246 will give you 216 over 77. This one is 0 minus 164, makes that negative 164. Then we have 8 times 77 minus 656 will give me negative 40 over 77. Now, so you have this is your AN right here. So obviously, now that's not a vector, that's just a scalar multiple. So to get rid of it, where we have n of 1, just multiply by the reciprocal, just like you would for any fraction. So I flip it over, multiply this by the reciprocal, and technically that's the answer right there where the n1 is. Meaning this is correct, so evidently I tried to get a little cute here. So this is right. This is just a matter I distributed and simplified. Oh, and one thing I did check too is that I checked that my N1 dotted with my T1. There's T1. I did dot those two together and saw that they equaled 0. But this, okay, I guess that's not that critical because it's technically correct right there. But yeah, obviously that doesn't prove my answer is right, but I mean the fact that it dotted to be 0, it has to do that or it's certainly wrong. So let's see, put it in maple, look at all that mess. and I was able to simplify it to get it to look like this answer. Now they rationalize the denominator, and some reason they took 4697. You know, and I saw this and did this in another video. Well, I found it odd. Oh yeah, I had another problem in another video where they broke the square root of 6 as the square root of 2 times the square root of 3. Well, I don't see the point in breaking down that number into 61 and 77 if you can't reduce it further. See, at least when I did this step up here, let me show you. At least, you know, when I did this reduction right here of 976, at least there was a reason to it. You know, at least that radical simplified into an integer. There'd be no point in breaking that down to the two radicals if one of them didn't turn into an integer. So I don't know. I certainly wasn't involved in the programming of Maple. All right, so let's see. So there's, let me go back up here. I jumped down too far. Yeah, so there's all that Maple mess, and just for the grins, I put the graph in there. So I only sketched part of the curve. I don't know why I have the curve dashed this time instead of, well, okay, whatever. But there's t of 1. That's a nice tangent vector. There's the normal vector. And then here's the acceleration vector. So in other words, if you took the an component, that would stretch this, and multiply it by n of 1, that would stretch this out farther. And then the ta of t would stretch this out farther, to where if you added them together, then you would have the a1 vector here. So here's another example. Looks like the same idea. You know, they're using the same hint that I'm using too, because they realize the complication for finding n. In fact, let me scroll back up here and look at the Maple just for a second here. Now maybe this could be combined a little bit. You know, some of this is a little bit, you could combine some exponents together that they're not actually doing in the problem, so that could have been simplified a little bit. But look at the, you know, principal unit normal vector, what it turned out being there algebraically. Not all that much fun, but like I said, I could have cleaned that up a little bit, I guess. They could have. And let's see. So I'm going to find a of 1 first. Once again, it's 1 is just coincidence. It's at 1 again. So first derivative of this will be 1, 2t, and then t, because it'd be 2t over 2. The next derivative would be 0, and 2, and 1. Well, since they're all constants, then that means the acceleration is constant. So obviously a of 1 or a of anything, there's no t to plug in. So it'd be 0, 2, 1. Now I'm going to find the tangent vector. So I'm going to put 1 into r prime of t, which would give me 1, 2, 1. And which makes the magnitude r prime of 1 be the square root of 1 plus 4 plus 1, square root of 6. Therefore, the unit tangent vector would be 1 over 6 times 1, 2, 1, which, of course, you know, you can distribute the square root of 6 there. It's correct either way. So the formula for a of t, well, there's more than one formula, but I like a dot t, especially since I've already found these two answers. A dot t. So once again, you can leave the scalar here and just dot these numbers. 0 times 1 is 0, 2 times 2 is 4, 1 plus 1. 1 times 1 is 1, 4 plus 1 is 5, so it's 5 over the square root of 6. So remember the a of t, you know, a of 1 here is a vector, but a of t at 1 is a scalar. Now I'm using the radical formula, but you could try one of those other formulas. Just don't use a dot n, obviously, but there's one where you had to do maybe the cross product one might not be so bad if you don't want to mess with these radicals. I believe it was the magnitude of v cross a divided by the magnitude of either v or v, I think. Yeah, If you think that one's a little better, you can use that one. And let's see. So 0, 2, 1, that would have a magnitude of the square root of 5. So it's the square root of 5 squared minus this number we just got here, 5 over root 6 squared, which is 25 over 6. So 5 minus 25 over 6 is 30 over 6, which makes that 5 over 6 under the radical. So it's the square root of 5 over 6. Or I just happen to choose to split the square roots out, which probably mean, we need to do when we're doing this algebra part right here. They need to be separated. So, but mathematically, it could have been all one square root with 5 over 6. So just like the last problem, we're going to just plug everything in and algebraically solve for n. So we have 0, 2, 1, which is a of 1. A sub t is 5 over root 6. T of 1 is 1 over root 6 times 1, 2, 1, right there. Plus a of n that we just found, square root of 5 over square root of 6, and 1. So I'm combining these components together. I get 5 over 6 times 1, 2, 1, which will give me 5 over 6, 10 over 6, 5 over 6. I will now bring this over to the other side. So 0 minus 5 over 6 is negative 5 over 6. 2, which is 12 over 6, minus 10 over 6 is 2 over 6. And then 1, which is 6 over 6, minus 5 over 6 is 1 over 6. And then we just multiply by the reciprocal to get rid of this, and we'll have n of 1. And I don't care about rationalizing, but I just sort of mentioned that the square root of 6 over 6 is the same thing as 1 over the square root of 6. So you multiply, so that this answer is good right here, if you don't have to rationalize your denominator. And I didn't show the work, but you can obviously double check that yourself if you want to. Dot that with t of 1 and make sure it equals 0. And then the bottom answer is just rationalizing the denominator. All right, so that concludes this video on tangent and normal vectors.